Okay, so what are even and odd functions? A function whose graph is symmetric with respect to the y-axis is called an even function. If a function f is even for each x in the domain of f, f of negative x will equal f of x. So this is the definition of an even function. Be careful. We're not saying an even degree function. We can have even degree functions that are even functions, but this isn't about polynomials, and degree goes with polynomials. This is just what makes a function even. So pretty much what this is saying is if you substitute a negative x value into the function, it is the same as if you had substituted the positive x value into the function. On the other hand, a function whose graph is symmetric with respect to the origin is called an odd function. And if a function f is odd for each x in the domain of f, then when you substitute a negative value in for x, you get the opposite of the functional value. It should be noted that most functions are neither even nor odd. Now, this may seem like a silly concept, but this is something that we're going to learn about today, but we're going to apply it to other functions as we go through the semester. And when we get into trigonometry, we're going to be learning some trig identities that connect back to these even and odd functions. So it's really important that you understand the definition. Okay, so to help us, we're going to rule of 4 each one. All right, so let's say we are looking at the function f of x equals x squared plus 1. The first thing we're going to do is we're going to prove that f of x is even using the definition. So I'm going to copy down the function f of x is equal to x squared plus 1. And then what I want to do is I want to show that if I substituted negative x in for x, I would come out with the exact same function because that's the definition. F of negative x equals f of x. So right here, I'm going to substitute negative x in everywhere I see x. And then we're going to work it out. So when we square negative x, it just becomes x squared. And then we still have plus 1. So what you notice is f of x and f of negative x turn out to be exactly the same. And so that's how we prove that a function is an even function. So let's make sure we state that. So since f of negative x is equal to f of x is an even function. And that is the algebraic method for proving or showing that this function's even. So let's look at it numerically. So when we're looking at it numerically, what happens is for every point that you have on the function, for every point, let's say we call it AB, we also have the point negative AB. And again, that's because if we substitute x in, we get the same range value as if we substituted negative x in. So let's look at the points on the function f of x equals x squared plus 1. If we were to pull some points out there, and I'm gonna use the vertex. The vertex of that, if you think about it, is at 0, 1 because that graph is shifted up 1. And then from there, it's 1, 2, and 2, 5. And we have negative 1, negative 2, negative 1, positive 2, and negative 2, positive 5. So you can see the 0, 1 doesn't matter because it's 0 can't be negated. But when I substitute in 1, I get 2. But when I substitute in negative 1, I also get positive 2. So it follows that definition. And graphically, we can see it too. If we look at it graphically, this is just our basic quadratic function shifted up 1. And then we go out 1, up 1, out 2, up 4. It's just our basic parent parabola shifted up 1 unit. And so we can see graphically that for every point, like right here, if you look at this point, you've got the point 1, 2. We also have the point negative 1, 2. And that's what makes it symmetric about the y-axis. So really the piece we're looking for when we look at it graphically is the fact that it's symmetric about the y-axis. And then verbally is just some of these things that we have discussed. It's symmetric about the that should say y-axis. Guys, make sure you fix that on your notes. It's really important. That was a typo right there. Make sure it says symmetric about the y-axis. So it's symmetric about the y-axis. Also, if it is a polynomial function, polynomial functions will have even powers on x. It may or may not contain a constant term. So anytime it is a polynomial function, it doesn't have to be, as long as all the powers on x are even, and it can have a constant term or may not have a constant term, because all that does is move it up or down, it'll definitely be an even function. But please understand, like, they don't have to be polynomials. Like, the absolute value of x is an even function. It is symmetric about the y-axis. All right, so now let's do it for an odd function. We're going to do the same thing. We're going to rule of 4. Rule of 4 is really important because if you can look at any concept algebraically, numerically, graphically, and verbally, you really understand that concept. And that way, if you're trying to work a problem and one method is not working, maybe you can pull out a different approach to understanding that problem. So for odd functions, the definition is f of negative x is equal to negative f of x. In this case, we're given the function f of x equals 2x cubed. So we're going to prove that this is an odd function. So first I'm going to start by writing down what we're going to do is everywhere we see x, we're going to substitute negative x and see what happens when we do that. So if we cube negative x, remember you always do your exponents before multiplication, that would end up being negative x cubed, and then we multiply it by 2, so we get negative 2x cubed. So what we notice right here is f of x is the opposite of f of negative x. They come out to be the opposite of each other, which goes with the definition. By the way, if you've never seen those 3 little dots before, we use those a lot in math. They're like the little 3 dots that make a triangle, and they just mean, you know, in conclusion, therefore. So since f of negative x equals negative f of x is an odd function. All right, some things that are verbally important about odd functions. Odd functions are symmetric about the origin. If you have a polynomial function, an odd polynomial function will have odd powers on x, and it cannot have a constant term. Because, guys, if we had a constant term on it, it would move it up and down, and then it would no longer be symmetric about the origin. So stretches and shrinks will not affect the transformation of odd functions, but shifts will. So you can stretch it and shrink it all day long, but if you shift it, that is not going to make it symmetric about the origin anymore. All right, and then numerically, what we're looking for if we have an odd function is for every point AB that we have on the function, we have the point negative A, negative B. So if we look at some of the points that we have on f of x, our example, this is just our cubic function stretched vertically by a factor of 2. So it still has that point 0, 0. But instead of 1, 1, it has 1, 2. And instead of 2, 8, it has 2, 16. Instead of negative 1, it has negative 1, negative 2. Instead of negative 2, negative 8, it has negative 2, negative 16. And you can see that it fits this definition. For every point AB, we have the point negative A, negative B. We can also look at it graphically. If we graph it, it's just that cubic function stretched vertically by a factor of 2. And I know it's kind of hard to see symmetric about the origin, but this is symmetric about the origin, and it might be a little easier to check the points to be able to recognize that. The mistakes that is sometimes made is students think in order for it to be an odd function, it has to pass through the origin, and that's not true. For example, y equals 1 over x, our reciprocal function, is an odd function, and it never passes through the origin. So just make sure you're always using the definition. All right. So for the next set of problems, what I would like for you to do, it says use the definitions of even and odd functions to prove, notice this says prove, so we need to be doing this algebraically, whether or not each of the following functions is even, odd, or neither. Remember, most functions are neither even nor odd, so don't think they have to come out to fit in one category or the other. All right, pause the video, and when you're done, start the video back. Pause now. Okay, so to do this, we substitute negative x into the function and work it out. In the first case, when we do that, we notice that we get negative x cubed plus 1. Well, it didn't come out to be the same function, so it's not an even function, and it didn't come out to be the exact opposite of the function, so it's not an odd function. So in this case, this one is neither. Also, if you look at it graphically, this is your cubic function shifted up 1. So it's not symmetric about the y-axis, because if it was symmetric about the y-axis, it would be a mirror image over the y-axis, and neither is it symmetric about the origin. So I'm not telling you not to use those graphical or numerical methods to back yourself up. I just want you to use the algebra to prove whether it is or not. So using the definition, number 2, when we substitute negative x into the function, we get the exact same function, therefore it's even. For number 3, when we substitute negative x into the function, we get the opposite of the function, so it's odd. And for the last one, we do not get the same function or the opposite, so it is neither. And again, if you think about it graphically, number 2, that makes sense because it's just a parabola shifted down 3 units. Therefore, it is still symmetric about the y-axis, which is what even functions are. If you do number 3, I know you don't know that graph right off the top of your head, but if you looked at it, you would see it. And then number 4 is a parabola, but because it has that linear term, that parabola has definitely been shifted over to the right some, so it wouldn't be symmetric about the y-axis or the origin.
Restrictions on the domain. There are 3 reasons why we do not have a domain of all real numbers for functions. The first is when we have a variable in the denominator. So anytime we have a function, such as a rational function, where there is a variable in the denominator, we need to check to see, is there a value that would make that denominator equal to 0? If there is, then it makes the function undefined, and that is a restriction on the domain. The second situation is if we have even roots. In other words, like a square root. We know that we cannot take the square root of negative numbers in the real number system. So any value that would make the radicand, or whatever's inside the square root, negative, cannot be in the domain. To figure this out, just take what's inside your square root or fourth root or any even root and set it greater than or equal to 0, and then work the inequality out to figure out what you are allowed to have for your domain. The third reason is logarithms. If we have a logarithm, we have to make sure that we find any values that would make what's inside our log 0 or negative, because we know that the domain of logarithms is only positive real numbers. All right, so how do we figure out domains when we are adding, subtracting, multiplying, or dividing 2 types of functions? All right, first of all, let's let the domain of the function f of x be a. And let's let the domain of the function g of x be b. If you add 2 functions, subtract 2 functions, or multiply 2 functions, the domain of these new functions that we have created is the intersection of the domains of the original functions. That means it has to satisfy both of the domains. So for example, if you had a domain of all real numbers, and then you had a domain of 0 to infinity, then the intersection of those domains would just be from 0 to infinity. However, when you do the quotient of 2 functions, it is a subset of the domain, the intersection of the domains, because we cannot divide by 0. So when we divide those 2 functions, we might have to add to the original domain because we know that we can't divide by 0. So any value of the variable that would make that denominator equal to 0 cannot be included in the domain. All right, so let's do some problems. So starting with the first one, it gives us that f of x is equal to 2x plus 3. This is a linear function, therefore its domain is all real numbers. So let's just jot that down real quick. This one has a domain of all real numbers. The next one, g of x equals 2x squared plus 5x minus 12, is a quadratic function. It's a polynomial function, so it also has a domain of all real numbers. So this makes this pretty easy, because the intersection of the domain of all real numbers with the domain of all real numbers is also all real numbers. So this would give us the function 2x plus 3 plus the function 2x squared plus 5x minus 12. And then all we do is add like terms. It's that simple. So the new function that we have formed would give us 2x squared, and then 2x and 5x would be 7x, and 3 and negative 12 would be minus 9. And this new function we created would have a domain of all real numbers, again because the intersection of all real numbers and all real numbers is also all real numbers. All right, so let's do the division one. So for this one, we have f divided by g of x. So in the numerator, we have 2x plus 3. In the denominator, we have 2x squared plus 5x minus 12. If we were able to factor the numerator and denominator and have a common factor in the numerator and denominator, we should reduce it. So you may want to real quickly just check. Obviously, the numerator cannot be factored, but if we were to factor the denominator, those factors would have been 2x minus 3 and x plus 4. So since we do not have a common factor in the numerator and denominator, we're done in this case. This is our answer. However, we have to now include the values of x that would make the denominator equal to 0 in our domain, because we cannot divide by 0. So since we have the factors 2x minus 3 and x plus 4 in the denominator, just set those equal to 0 and solve, because we know that they cannot equal 0. So therefore, x cannot equal positive 3/2, and x can also not equal negative 4. So in this case, we have to add that to our domain. So our domain for this one is going to be from negative infinity to negative 4, in union with negative 4 to 3/2, in union with 3/2 to infinity. In other words, all real numbers except for negative 4 and positive 3/2. Okay, so let's apply that to finding the domain for functions that have already been put together. So starting out with this first one, we have to ask ourselves, is there a variable in the denominator? Is there an even root radical? Is there a logarithm? If none of those things apply, then the domain is just all real numbers. All right, starting out with this first one, since there's a variable in the denominator, we know that the denominator cannot equal 0. So we set the denominator equal to 0, or in other words, not equal to 0, since we know it can't equal 0, and we solve. So we would add 7 to each side. 2x cannot equal 7, divide each side by 2, x cannot equal 7/2. So therefore, the domain is all real numbers except for 7/2. So we would say the domain is from negative infinity to 7/2, in union with 7/2 to infinity. Okay, so for the second one, we have a square root, and we know that whatever is inside that square root cannot be negative. Therefore, whatever's inside the square root needs to be 0 or positive. Anytime you have one like this, all you have to do is take the radicand, which is what is inside the square root, and set it greater than or equal to 0. That is what we are allowed to have. So any values of x when we solve this polynomial inequality that work will be in the domain. Remember, guys, for polynomial inequalities, you first have to find your zeros. So that we know when we factor this, this is x plus 3, x minus 3. So the actual zeros are at negative 3 and at positive 3. We then draw our number line, place our zeros in order on the number line. Because we do want to know when this is equal to 0, we put closed holes at negative 3 and at positive 3. And then graph the function, the corresponding function, using end behavior. This is a parabola, it opens upward, so it would look like this. We want to know when this function is greater than or equal to 0, so that's when it's on or above the x-axis. So we would shade the number line when we're less than negative 3 and when we're greater than 3. Therefore, the domain of g of x is going to be from negative infinity to negative 3, bracket, in union with 3 to infinity. And you can always check yourself out. If you were to take a number like 0 and substitute it into this function, we would end up with the square root of negative 9. And we know in the real number system, we cannot take the square root of negative 9. So you can always kind of test your domain and make sure that it works out. Okay, looking at the next one, this is one where we have to apply the intersection of the domains. We have to find the domain of the numerator, the domain of the denominator, and then make sure our domain satisfies both of them. So in the numerator, we have a square root. Therefore, x must be greater than or equal to negative 5. In the denominator, we know that the values of x that would make the denominator equal to 0 are not included in our domain. So we'd factor the denominator, which gives us x plus 1, x minus 6, and therefore we know that x cannot equal negative 1 or positive 6. So we now have to put all of that together because it has to satisfy the fact that x has to be greater than or equal to -5, and also x cannot equal -1 and x cannot equal 6. So in this case, our domain is going to be from -5 up to -1 in union with -1 to 6 in union with 6 to infinity. And folks, that is saying all real numbers greater than or equal to -5, excluding -1 and +6. Okay, why don't you pause the video, try the next three, and then see if you're getting them correct. All right, so looking at k of x, this is one where they put two of the three things together. Not only do we have a variable in the denominator, we also have an even root in the denominator. So we know we can't take the square root of a negative number. So if it had just been the fact that it was the square root, we would have taken x minus 3 and set it greater than or equal to 0. But we also know that the denominator cannot equal 0. So if we put those two things together, x minus 3 has to be just greater than 0 to figure out the domain. It can't be negative and it cannot equal 0 since it's in the denominator. This is just a linear inequality, so we would just add 3 to the other side, so therefore x must be greater than 3. Our domain would be from 3 to infinity, not including 3. For the next one, we have a logarithm, and we know that whatever's inside that logarithm has to be a positive real number. So we take what's inside the log, and we say that must be greater than 0. Again, it cannot equal 0 or be negative. Again, we have a linear inequality, so just solve it, subtract 1 from each side. We get the negative x is greater than -1, multiply or divide each side by -1, therefore x is less than +1. Make sure when you do that you flip that symbol. So in this case, our domain is from -infinity to 1. Guys, all of these problems you should be completing without a calculator. You have to be able to find domains on your own by the knowledge of functions and your properties and your rules. You cannot be graphing these in the calculator and then looking at them to get this. All right, the last one, the problem is we have a variable in the denominator. Since this one is not factorable, what we would do is just take the denominator, what's in the denominator, and set it not equal to 0. When we try to solve this one, we get x squared cannot equal -6. We would take the square root of each side. So we get that x cannot equal plus or minus 6i. Well, in this case, that's not a real number. So actually in this case, folks, there isn't a real number that would make the denominator equal to 0. Therefore, the domain is all real numbers. And you can sit there and play with this. There is not a value of x that would ever make this denominator equal to 0. So I want you to understand that just because there's a variable in the denominator doesn't mean that the domain will always have a restriction. Most cases it will have a restriction, but not always.